theirs where no one else is.
Hey there, YouTubers. Welcome to my channel. Today we have a special on quantum mechanics where we're going to be solving the Shrodinger Equation in 8 dimensions. Excuse this background sounds in the room, please, YouTubers. I'll think of a name for you guys soon enough. I'll call you Kyle's Kittens or something. Okay, so what we have to understand is most important thing is the Shrodinger Equation of quantum mechanics. Shrodinger Equation. I'm right. It's a G. That's not a Q. It's supposed to be a Q. So we're going to keep this under 20 minutes today, guys. Nice and short video. So what that Shrodinger equation is, very simply, it's just H psi equals something quantum. No, I'm just kidding, guys. It is, oh, we're getting some auxiliary light in here, everybody. Woohoo! H psi equals E psi. That's it. That's all you need to know. 4 letters. You could write this equation on 1 inch. That's important. It's the more inches are in your equation, the less useful it is. That's something that you can apply to all things. The more inches it is, the less useful it is. So let's just go ahead and label these parts real quick. This H is Hamiltonian. What is Hamiltonian? Hamiltonian. This is named after Hamilton, who did some stuff with mechanics. In this sense, it's essentially the function or matrix that represents the total energy of a system, which is generally going to be kinetic energy plus potential energy. Then we have over here, this is an eigenvalue equation, by the way. This over here, this E are the energy values. These are just like numbers. You guys know any numbers? Examples of numbers are 6 and 20. Those are numbers. And in general, these energy values are discrete numbers in a discrete set, not a continuous function of energies. And then the only other thing here is this thing here, psi. Now, psi, also known as psi, is the wave function. Think of a beach. Think of a beach with waves. Now, it's not like that at all. Instead, the amplitude of this wave at any given point represents the probability density. So how likely it is that an object is at that point in space. So since it's the density, to find the actual probability, we have to square the wave function and then multiply by the distance in the spatial coordinate to actually get the probability for a given spatial location, which of course brings us to calculus, if you will. It's an integral over space of the function squared multiplied by a differential element in the spatial coordinate. But that about does it conceptually for the equation. Everybody stay tuned for part 2, in which we'll work through an example of this equation for a physical system. All right, thanks guys.